This is what we're going to talk about today. It's a lot, and they keep making the sessions shorter and shorter and shorter. So if we're lucky, we'll actually finish this today. This is a deep dive talk. This is not an introduction talk. If you're hoping for an introduction talk, this might be over your head. But what we're trying to try and do is we're going to try and really walk people through peeling back the layers of the onion of how search requests are handled. We're going to start with two examples dealing with like a single Solr node, single core, a really simple query, and then a facet query and how that makes things a little more interesting and complicated. And then we're going to look at essentially the same two queries in Solr Cloud and how we deal with multiple shards, multiple replicas. And I'll briefly talk about like where things are plugins, so where you could sort of hook in if that's not already obvious. Although, frankly, if you saw Jan's talk earlier today about the plugin ecosystem, I am super fucking psyched about that, and hopefully that'll make all this a lot easier. Anyway, like I said, this is not an introductory talk. Is there anybody in the room who doesn't understand the syntax up here? If there's anything on this slide that you don't understand, this talk is going to be over your head. I'm sorry. Like, don't waste your time. I will not be offended. Get up and leave and flip me off on the way out. I don't care. But if there's anything on this slide that you're looking at and you're like, I don't know what that means, this talk's probably going to be over your head. Okay? Just fair warning. So let's talk about what happens when you do this query. Well, actually, I lied. First, let's talk about what happens when you start up Solr. When you start up Solr from the very beginning and you run, bin Solr, -e, tech products, whatever, right now what that does is it actually spins up Jetty, and Jetty spins up internally a Solr web app, and that Solr web app says on startup, I need a dispatch filter, and that dispatch filter says I need a core container, and the core container says, oh my God, how many cores are on disk? And it spins up those, and then those, so on and so on. It's turtles all the way down. So when the request comes in, right, when you actually do that query that we just talked about, when you say, hey, I want to search for iPod, the Jetty layer handles all the HTTP communication. And at the HTTP layer, it's listening on port 8983, and it's saying, hey, I got a request. It's bytes on the wire in HTTP. I am going to convert that into a servlet request, which has parameters, and it has, I don't even remember what they're called because I haven't worked in servlets for so long, but it has all that data at an HTTP layer. And that is an abstraction that we in Solr don't want to have to deal with, and it is an abstraction that might change. We might switch to Netty later. We might get rid of servlets. Who knows? It's an implementation detail. But by the time Solr proper really gives a shit is when the Solr web app gets it, the Solr dispatch filter deals with that HTTP request, and it starts to sort of peel those layers and treat them as Solr objects. And the first thing it does is it looks at that URL and it says, tech products, what is that? Do I have a core that corresponds to the name tech products? If I don't, fail. If I do, if the core container says, yes, there is a core named tech products, great. Hey, tech products core. The next part of my path is going to identify a request handler. Do I have a request handler named select? And the core is going to say, yes, you do. Great, I am not going to fail. And then it goes and executes the request handler, gets the response, and it says, great, now I need a response writer. I don't have one in the URL, so it defaults to JSON. Hey, core, do you have a response writer named JSON? Great. Now I know how to take that request and response, serialize it to bytes back over the wire, and everything's done, talk is over. But there's more to it, obviously, right? I glossed over the request handler, and that's where 99% of the logic is. So let's talk about that. Let's talk about what happens. Let's talk about now what we've identified, and we've gone from the HTTP layer to Solr objects, what we're doing. I don't know who that is, but he's loud. I thought I was loud. Jesus Christ. When I can hear somebody else over me and I'm on a speaker, fuck. Okay, so request handlers. This is the first type of plugin we're going to talk about, right? And to people on this side of the room, sorry, but this is the screen closest to me, so this is the one I'm going to point at and look at, and I don't know what you're watching. Hopefully it's sports. Request handlers are the first sort of plugin that we're really going to deal with. You could write your own request handler, but 99% of the time, you're going to either be dealing with the search handler or the update handler. We're not going to really talk about the update handler because that talk didn't get accepted. So we're going to talk about the search handler. Search handler, Search handler does almost nothing, literally. Search handler does virtually nothing. What it does do is it loops over what we call search components. And for every search component, it calls two methods, prepare and process. Prepare's job is to validate input and fail quickly. Process's job is to actually do some work. all that the search handler really does, other than loop over a configured list of components, all it really does is layer on what we call init parameters now. I'm not really a fan of the name, but it's basically a way of sort of setting either some defaults or some invariant rules on how request handlers are dealt with. So for example, when the query component goes to call its prepare method and look at what things got passed in as part of the request, it might see a def equals text parameter or default field equals text, even though that was never part of that request, right? We never specified that here, but that's because the search handler can layer that on. And it's completely transparent. The rest, from that point on, once search handler says, okay, for /select, what parameters, what initialization do I need to apply to this? From then on, all other plugins, all other components, they can't tell that any different from something that the original HTTP URL included, right? So let's look at the query component, the prepare method. This is where like most of the work happens. And it's all validation. It's all parsing. It's all let's sanity check that the user knew what they were doing and I shouldn't fail fast. So we get some very basic checks up first, things like start and rows parameters. Are those numbers? You know, or did they say rows equals lots, in which case fail quickly? No, it said it's a number. Is it a positive number? Yes, great. We're good. Everything's okay. Next, we look at things like the field list. Are those actual fields in our schema here in orange? You know, are they real? Do they exist, either dynamically or statically defined? We want to validate that very quickly. Before we do a bunch of work on a search, let's make sure we're not going to error out as soon as we try to respond to those results. And those field names are schema fields, but they, again, map to a type of plugin, field types, which have analyzers. Most people are pretty familiar with the schemas and the various things that you can plug in and configure with schemas, so I'm not going to peel back too many layers there. But we validate that those fields exist. We also need to parse the query, right? And before we can actually parse the query, we have to decide which parser we're going to use to parse the query, which is another type of plugin here in green, the query parsers. The default query parser is called the Lucene Q parser. We're going to look for a parameter called def type to figure out which parser to use. Again, it's a plugin. You can customize it. But if there isn't one specified, we're actually going to look at the query parameter itself to see if it has the local parameter syntax at the beginning, which will tell us which parser to use. But that parser's job is to say, well, what do I know about the request? I know things like default field equals text. I know what my query string is. I'm going to use that to determine what query object to build. And in our simple example of iPod, it's just going to build a simple term query. But the reason it's going to build a simple term query is because it took that default text field in orange and it mapped that to a underlying field type in purple, which was also conveniently called text because we can't come up with good names for shit, so we reuse words over and over again. But that default text field, default text field's type of text has an analyzer associated with it. And that analyzer is very simple. It just lowercases the term. So iPod lowercase is iPod. Great, now we have a term query. We're ready to go. We're ready to run that query. The only other thing we have to do is decide how we're going to sort those results. So we parse that sort. We see that the in-stock field is a Boolean. So we say, hey, bool field, how do I sort descending, right? Descending? Yeah, good. All right, I remember my own slides. How do we sort descending bool field? That gives us a sort field object. And likewise, score. Well, score is a magic keyword. The query component knows that, so when it parses that, it doesn't bother dealing with the schema at that point. It just creates a, it doesn't even create it. It's a singleton, essentially, a sort field.score object. And those two things are bundled together. Now we have our sort. So we have the things, the main things we need to execute the search, which are start parameter, row parameters, the query to run, and the sort. We're good to go. So now the process method gets kicked in. And the process method says, Solr index searcher, here's a bunch of shit, go do a search. And the Solr index searcher says, will do, I will execute that search. Ultimately, what the query component wants back is something called a doc list, at which point I will pause for dramatic effect. A doc list is a very small data structure that represents one page of results. And when I say results, it's not even the interesting parts of the results. It's really you can almost think of it as two arrays. One of the arrays is an array of integers, the internal IDs of the documents that match on your first page of results. The second array is an array of floats, the scores of those documents. And then there's like two little bits of metadata, which is the total number of documents found and what page am I. That's all a doc list is. Super small, very easy to cache, very easy to hang on to. And the Solr index searcher, when you execute that search, it's going to loop over the index reader and the inverted index. It's going to execute that, and for every match it finds, it's going to record that information. But it's not just going to record page 1, right? Our start parameter was 0, our rows parameter were 10. There might be millions of documents that are indexed. It's a lot of work to check all of those documents against the query. So the Solr index searcher has caches to try and take advantage of the fact that if you ask for page 1, you might ask for page 2 as well. So that's what we call a window size, or a search window. That's a configuration option that a lot of people know about, so yay, you're here, you just heard about it. There is something called a window size, or window result size, or I don't know. It didn't fit on the slide, so I had to rename it, but we're gonna call it window size. You'll find it in Solr config XML. And what it basically says to Solr index searcher is when you're gonna run a query, there's a minimum size of things to put in that query result cache. There's a minimum size of things to ask for because they're really tiny. I think in the tech products example, it's set to 20. So when you say start equals 0, rows equals 10, it looks at those values and it looks at the configured window size and says, well, what is the actual minimum that I want to compute? And it's 0 to 20 instead. So when it goes and executes that search and it executes that query on the underlying index reader, it doesn't just find you the first 10 results, it finds you the first 20. And that's what goes in the query result cache. So the next time that query comes through, you'll get a cache hit. Ultimately, though, what the query component cares about is only that first 10 results, because that's what it asked for. So that's what Solr index searcher returns. And the query component says, I am great, I am done, I have everything I need. And we pop back up the stack to the dispatch filter that we talked about before, somewhere, yeah? Who says, what was it? Response writer, great. I now have a bunch of data, I have a bunch of objects, but now I need to send that back to my HTTP client over the wire. This is where the response writer comes in green. The response writer's job ultimately is to take whatever data has been created by our request handler and convert it into bytes. The default format is JSON, it could be XML, it could be Java bin, you could write your own, it's a type of plugin, but ultimately its job is to say, what do I have, how do I convert it to bytes? And in this kind of a simple query where all we really have is a doc list, its job is to say, okay, well, I'm going to loop over all those documents, and for each one, I have to now go get the stored fields, which are not in my doc list, because the doc list is really small. It's just those internal IDs. But now I need to go ask the searcher for the stored fields of each of those documents, which the index searcher, this is the stored fields are in purple. It's going to go get those from the index reader, or it's going to go get them from the document cache, which is there in case that document gets reused. You know, it's a very popular document. If it was 1998, it might be the iPod, which is what we're searching for in our super cool, hip, trendy data set. But that document might be in the document cache because it's very popular and it shows up in lots of searches. But that is the JSON response writer's job, is to loop over those documents, get their stored fields, take those string values and figure out how to serialize them to bytes. And Bob's your uncle, we're done with the request. Right? Make sense to everybody? This is where you all say yes. Woo! All right. So now let's get really fucking crazy. No, hopefully this is also really straightforward and you all understand this and there's no big surprises here. All I've really done is I added a filter query on price. I made the sort more interesting. Now we're sorting by a function. I've added faceting, and I've also added a what's called a doc transformer to the field list. If you see there, Y. I made a pseudo field called Y, which is going to use the explain transformer. The first thing to know about this is that at the HTTP level, at the web app level, at the dispatch filter level, all of this is the same. Nothing changes, right? In terms of picking a request handler, we're not doing anything different. This request is exactly like the last one. Where things do start to change is, I mentioned the search handler loops over components and it executes them. Well, when it loops and gets to query component, we do all the same things we did before, but we have a few more things that are very similar to what we saw. When it's parsing the filter queries to build up filters, it again goes and looks at the schema and says, you know, okay, I've got a query string, I need to parse it, I use a query parser. Oh, price field is a number. I need to do a range query on a number. The field type tells it, how do I do a range query on a number? What's the data structure look like? What's the query object look like? Nothing too surprising there, but I wanted to include it for completeness. There's an N in that word, right? Yeah, okay. But the other interesting one is the sort. Now we're sorting by a function. This is another new type of plugin, which is called a value source parser. You can have lots of these. Solr has something like 100 of them. Just basic math functions, divide, sum, addition. Sum and addition are the same, but both keywords are supported. Multiplication, exponents, things like that. Ultimately, those, well, not ultimately. To start with, those each map to a small plugin, right? So divide maps to a divisor value source parser, which knows that it's going to wrap two things, and it's going to take one and divide it by the other. Those could be composed of other functions, of other functions, of other functions. But eventually, as you go turtles all the way down, there's got to be a field at the bottom. And those, again, come from the index schema. Those functions say, hey, index schema, the popularity field, I need to know some way to get a value source out of it. I need to know some way to say, for every document, what is its numeric value? And that's, again, a function that we'll get out of our field types. But that's what the query components prepare parser does, or prepare method does, is it has to do that extra level of parsing. It has to do that extra validation to say, can I actually divide a popularity by a price? Are those both numbers? If I tried to divide name by price, I would get an error very quickly before I waste a lot of time on that search. The second thing that happens that's very different in this request is because I did turn faceting on, now the facet components prepare method actually does some stuff. In that first request, I didn't even bother to mention it because it would immediately return. It would just be like, nope, done. In this case, it says, oh, wait, that URL has facet equals true. Okay, I have some work to do. It validates that the field you want to facet on, the cat field or category, it validates, is it in the schema? Is that orange cat in a schema field? Yes, it is, great. And then it sets a little bit of metadata on the request. It says, hey, I need a doc set. Pause for dramatic effect. So I talked about a doc list before, right? I said it was a very tiny object that just represented one page of information, right? Just the internal IDs and their scores. A doc set is completely different. A doc set is almost, well, not almost, in practice it usually is, a bit set of your entire index, unsorted documents, but the bit is set if that document is in the set, right? So of all the documents that match our query, right, regardless of score, regardless of pagination, set a bit for every document that is matched to our query. And when the facet components prepare method sets that flag, it doesn't actually do any work. It doesn't generate anything. It's just informing the Solr index searcher that when query component goes and executes that query, which again, from query component's perspective, this looks exactly the same as the last query. But the Solr index searcher now knows that it needs to generate additional information. It doesn't just need to generate that doc list because there's other actors in play. Query component is not the only kid on the block. Now facet component is involved as well, and facet component wants some shit. So when Solr index searcher does that query and it iterates over and says who matches, who doesn't, what's their score, who's in the top 10, in addition to generating that doc list and putting that doc list in the query result cache, it's also generating a doc set. It's saying facet component needs to know not just about this page, but about everybody who matches, which usually winds up in the filter cache. And when it's all done, query component says, great, I'm done. We're ready to respond, right? We're ready for that response writer to write our results out. And facet component says, slow your roll. No, I have some work I want to do. So the process method for facet component says, all right, I'm faceting on the category field. Hand wavy, there's optimizations here, but essentially it says, index reader, for the category field, I need to know every term. I'm going to loop over those, and for every one of those, I'm going to get at the doc set of every document that has that category, electronics, DVDs, pool supplies, whatever it is. I'm going to take that document set, and I'm going to intersect it with the one I got from query component. And that's going to give me my count for my facet results, right? And then, and only then, does the response writer say, now I've got all my data. I've got a doc list in red, but I've also got facet counts, which are also in red. Why is doc list in orange? Oh, because it comes from the inverted index. Yeah, I'm colorblind, apparently, because that looks red to me. Anyway, so that's what the response writer is going to write back. It writes back the document list, and it writes back the facet counts. It's in charge of figuring out how to take those objects and serialize them as bytes in JSON. But we also have that one little thing I mentioned, the Y pseudo field here. That is what we call an augmenter or a transformer. So it's the last type of plugin I'm going to mention, I swear to God. Pretty sure. And it's something that's very delayed deferred binding, right? When the response writer is looping over that doc list, it sees that it has a list of fields it needs to write back, and most of those are real field names, so it goes and gets the stored field. But when it sees that Y pseudo field, it sees that that maps to an augmenter or a transformer, in this case the explain transformer, and it says, okay, well, for every document, I'm gonna execute that bit of code with that internal document ID. It can do whatever the hell it wants, and whatever it gets back, I'm gonna include in that document as if it were a field. So in this case, the explain augmenter goes and asks the index searcher, hey, explain to me the score. Give me a data structure that explains why that document got the score the way it did. From the purpose of the response writer, though, it's just a plugin. It doesn't care what it did. Then we've got ones that do child doc queries or arbitrary subqueries or debug information or value constants. It's just a special type of plugin that the response writer can use. Okay? With me so far? No one ever said this was a low-key talk, right? All right. So those were our simple queries. Everybody feels like they're simple, right? Everybody feels like those were totally straightforward. Now let's talk about cloud queries. So we're going to go back and we're going to look at our simplest query from before, but we're going to look at it in the context of 4 nodes with 2 shards and 2 replicas, right? Which is kind of the basic reliability factor. You've sharded, you've got some recovery mechanisms in place, and you've also you're able to scale a little horizontally. So this is the time when we actually have to start having an interesting conversation about HTTP, okay? Because now we have a higher level that we have to deal with. Because the very first question is, what node is that query even going to go to, right? So if we imagine that we've got our 4 nodes and we've got our 2 shards, 2 replicas, that basically means there's a total of 4 cores somewhere related to our tech products collection. And maybe, by dumb luck, 1 node has 2 of those cores, and 1 node has none, right? Woo! All right, I'm not going to do that again. So if our request goes to host 1 or if our request goes to host 4, everything's fine. We have exactly 1 core that relates to our collection, and that's the core that we're going to say, hey, do some work for me. If our request goes to host 2, way up there in the corner, we're also fine. It just has to randomly decide which one of those 2 cores to execute the query. If it goes to host 3, though, this is where the dispatch filter starts doing interesting things. The dispatch filter knows that it's running in cloud mode. It knows it can talk to Zookeeper via the core container. And as soon as it says, hey, I've got a URL with /techproducts, I need a core that corresponds to that collection, then it sees, no, it doesn't exist. Or more specifically, it does exist, it doesn't exist here. So it's not a failure case, right? It is a valid collection name, but I personally, on host 3, don't have a core for this. So without even unpeeling the HTTP layer, it acts as a proxy and forwards it to a node that does, right? That is the first port of where Solr Cloud makes this query more interesting, is that if that request goes to host 3, it's going to immediately act as a proxy and forward it to insert any random host. But in this case, I said host 4, because why not? It made the line easy to draw. So when the request gets to host 4, though, remember, we're sharded, right? We've got 2 shards, shard 1 and shard 2. Host 4 only hosts a copy of shard 2. It has shard 2 replica 1. It doesn't have the whole index. So our query can't be as simple as the examples we've seen before, because it can't just do a search across its local index. That'd only be half the data. So what that shard on host 4 has to do is act as a coordinator and query both shards, right? Which means that search handler now gets more interesting. In the single node case, I mentioned search handler is really dumb, and all he does is loop over some shit. In a Solr cloud query, search handler starts to act as a coordinator. Instead of executing the simple prepare and process methods of its components, it actually loops over all of the components executing a distributed process method. The distributed process method gives those components the opportunity to say, I have information I need to ask of other instances of myself on the shards. So here is a shard request I want you to execute. And search handler will say, okay, I've got some shard requests I need to execute. When I get the responses back, I'm going to go do those in parallel. And when I get those responses back, I'm going to loop over all the components. And I'm going to say, hey, how do you want to handle these responses? And the query components or search components will say, okay, well, I've got the information I need now, thank you. And then the search handler will continue that loop and say, okay, do you need any more information? And if so, what is it? And it'll keep doing that as long as those search components want information. And when it's all done, then it will assume that it has accumulated everything it needs, and it can merge all that data and return to the final client, right? So in this really simple example, right, remember, this is just a query for iPod. That's all we're doing here. The first thing the search handler does is say, query component, what do you need? And query component says, well, in order to know the top 10 results that match iPod, I need to ask a copy of the first shard for its top 10, and I need to ask a copy of the second shard for its top 10, and then I'm going to merge those. I'm going to merge them by the sort fields. So the very first thing I need is the top 10 IDs, and for each of those IDs, I need the sort values, because otherwise I can't merge them. I don't know, should they go like this, should they go like this, where, how do they line up? So search handler says, great, I'll execute that query, and that's what I've called the alpha stage, right? That's in green. So for shard 1 and shard 2, they both get identical queries that say, hey, a query for iPod, I only need the ID field, but we've got this new special internal parameter, FSV, which is the field sort values, even though they might be functions, whatever. And what that returns, what shard 1 returns and what shard 2 returns, is the top IDs and their sort values. And then query component handle response method, which is a mouthful, will merge those, and I'll show you an example of what that looks like. And then search handler says, okay, well, you're good, right? You're done. Not exactly. I have to do a beta request, because now that I've merged them and I've decided what my real top 10 are, I need to go back and fill in the rest of the field list. I need the name field, right? Because we didn't bother asking for that in the alpha request, because if we needed like 500 fields, we don't want to ask for it from every shard for a bunch of data that we might throw away. So that's where that beta request comes in and says, great, now that I know which documents to return, now I need the field list from all of them, right? And when shard 1 and shard 2 get these alpha requests and these beta requests, those look exactly like what we saw before, right? The response writer kicks in, the stored fields, the caches, all of that. But the coordinator, he's not dealing with the index searcher at all, right? He's only sending these distributed queries to shard 1 and shard 2, even though he is in himself a shard or a replica of a shard. He doesn't care. His job is to just be a CPU workhorse and coordinate the merging, right? And that merging in this, in our example here, might look something like this, right? Shard 1's results might be A through G in this particular order, and shard 2's results might be Z through something in reverse that I don't remember because I don't know my alphabet. But ultimately, when it's merging, it says, okay, well, I need 3 from shard 2, and I need 7 from shard 1, because when I merged those results, when I looked at those sort values and actually did a sort merge across them, then my final result is over there, that mixed column of letters. But all I have is the IDs. That's where that beta request comes in, where I ask shard 1, what are the name fields for A through G? And I ask shard 2 for X, Y, and Z, what are the name fields, right? And I can merge those results. Does that make sense to everybody? Yes, okay, so the question was about the score and the TF-IDF of the local. That is true when we are doing the individual searches, right? When we've executed those when we've executed the alpha queries against shard 1 and shard 2, it's going to compute a score, which may be something we're sorting on, but that score, regardless of whether we're sorting on or not, that numeric value that might be returned, that is very much local to those shards, except that we also have a distributed stats component, not component, what do we call that? Ansham, what's it called? Distributed stats cache, right? Or the exact stats cache, what did you call it? You named it. All right, exact stats cache. I glossed over it here because it gets really into minutia, but it is possible to configure your nodes so that when they are computing the scores and thinking about TF and IDF and all that, they're not just looking at the local stats of their local copy of the index, they're actually looking at the whole collection. It's an overhead, it's an extra bit of communication that has happened, but it is possible, it's a good question. But yes, if that score is then part of the sort, that can affect how these things are merged, how we decide whether document, Z appears above document F, things like that, right? Okay, so that was our simple query with our multiple shards and how we can merge those, right? Because that's a very straightforward kind of merge sort, right? We've got top 10 here, top 10 here. Are they like this? Are they like that? We figured that out. In our more complex query, things get more complex. Big surprise. I will point out there's an asterisk here. This is not as complex as the last complex query we did because a lot of it doesn't matter. I got rid of the filter query. I got rid of the document transformer because in a cloud situation, nothing is different about how those are executed, right? Those are still things that apply when, in the case of the filter query, they only apply when doing the search on the individual shard because they're very much local to the documents. And likewise, the response writer, when he's executing that doc transformer, those happen on a per document basis. So the individual shard executes those transformers, and at that point, they're just regular fields. So the coordinator doesn't know or give a shit that that was a doc transformer as opposed to a stored field. It just knows that it's data that comes with. So for the purposes of talking about how cloud queries are interesting, all I've really done is add faceting to our simple query, which makes things a lot more complicated because unlike the merging of the query results in the top 10, you can't really merge facet counts that way, right? But I'm getting ahead of myself. When the coordinator gets this query, right? When the coordinator gets our basic query with faceting, everything that query component does is basically the same, right? Search handler says, hey, query component, do you have any distributed requests that you want me to execute? And the first time through, it says, yes, here are my alpha requests. I need the top 10 IDs from each shard with their sort values. And search handler's like, great, I will get that for you. But before it executes those queries, it asks facet component, distributed process method, do you have any data you want me to get from each shard? And facet component says, yes, I need to facet on the category field. I also want to over-request my facet counts, and we'll explain why we over-request in a minute. But what's interesting is it doesn't return new shard requests, right? This abstract concept I've got up here called a shard request. It doesn't create new ones. It actually piggybacks on the ones that query component created. So query component has said, I've got two shards, shard 1 and shard 2. This is the request I need to send to each of them. Facet component says, oh, you're already going to send requests to shard 1 and shard 2? Great. I need additional information. So what shard 1 gets for the alpha request looks like up there, combined with what's down here. I've kind of changed my diagram. I tricked you. You're looking at only shard 1 in the right column, right? There is no shard 2. But it gets a lot of parameters. It gets the query parameter for iPod. It gets the FSV equals true. But it also gets facet.field equals cat and facet limit equals et cetera. So that when shard 1 executes that alpha query, it looks a lot like when we executed a facet query before. As far as shard 1's concerned, it's just doing a regular search with a facet and computing all those counts, okay? And when the results come back from shard 1 and shard 2, search handler says, okay, now what do you guys need? And again, query component needs the same thing it always needed. It says, well, I can figure out how to merge these IDs, but I need the full field list. I need the names. So I need to execute this beta request where I ask for specific IDs and I get their name field. And facet component says, I need to piggyback on those requests, right? I need additional information. And since you're already sending a special request to shard 1 and a special request to shard 2, where you request specific info about documents, I'm going to also piggyback on that and request specific info about terms. Because the way the facet component merges is a lot more complicated, right? If this was the alpha results, right, from our initial facet counts where we got counts and terms from each shard, we cannot just merge those lists because unlike documents where we know a document only ever exists in one shard, a term probably exists in multiple shards, right? So at a basic level, what we want to do is add those up. And if you look at the green example is lawn, right? Lawn is in the top end results that we got back from both shard 1 and shard 2. So when we merge that into the middle column there, we know that lawn's count across the entire index for the facets is 190. That's an exact number that we have. But auto, we don't know. We only got auto from shard 2. We only got games from shard 1. But that doesn't mean we don't have some idea what the final count is because we know what our cutoff point was, right? We know that of all the counts we got, shard 1, the last count it gave us was 3, which means any term that shard 1 didn't give us is at most 3. Because if it was any higher, It would have been included in the data we got from shard 1. Likewise, we know that shard 2, the last value it returned to us when we over-requested our facets, was 90. So any term that we didn't get from shard 2, like games, it's got to be at most 90, because if it were 100 or 200, it would have been in our top n. So that lets us create this sort of informed, merged facet intermediate result in the middle there, right, where we can sort by the probable values. I'm not going to cough again, I swear to fucking God. Okay, that lets us sort by the maximum possible value or the minimum possible value. To be honest, it doesn't really matter, because we're going to go through that list and say what terms are candidates, what terms might be in our final top n that we don't have complete counts for, and why. So in the case of auto, it looks like it's our number one result, and it will probably almost certainly be in our top n, but in order to give an accurate count, we still need to know from shard 1 what was the value of auto. And likewise for games, games is on the cusp. Games looks like it's in our top n, but maybe not. It really depends on what the value is from shard 2. So when we're doing that beta request, when query component is asking for the name field of every document, the facet component is saying, yeah, and while you're at it, please tell me, shard 1, the count of auto and food. And while you're at it, shard 2, please tell me the count of games. And when it gets that data back, it merges it in with the model it's already built from alpha to compute that final list. And whereas here we were over requesting, right? N is what the user actually wanted. Facet.limit equals 100 or something. We over requested specifically so that we could catch that long tail, like in this case, DVDs. DVDs we know has a final count of 102. That might actually push it right up into that top 100 because games and food drop out because their values are low from one shard or another, right? This is weird shit, I'm not gonna lie, but most people are nodding. So I assume this makes sense. This is, to me, this is fucking the coolest thing in Solr, personally, but I could be wrong. Hopefully you guys are like, wow, that's interesting shit. But if not, or if you don't understand it, you can grab me afterwards. But the point being, this is where most of the complexity comes in to a Solr Cloud type query, right? I talked here about faceting, but you've got a lot of similar logic and a similar piggybacking requests that happen with highlighting, that happen with stats. When you do a pivot facet, this type of two-phase alpha beta logic, where we do one request and then in the second request we backfill data, pivot faceting actually does that in a recursive way. The deeper your pivots get, the more it might do secondary queries, and each time it's backfilling more and more information. It's really cool, but that's the general concept of how a cloud query runs, is that this search handler is saying to all of the components, what do you need? Do you need more? Are you done? Can I actually stop and give the user results? Oh, no, you want more stuff? Okay, great, I will get you more stuff. Hey, every other component, I'm gonna go get more stuff from every shard. While I'm at it, while I'm on my way to the store, is there anything else I can pick up for you? And if there is, we can save a lot of time, we can save a lot of work, and we can do one request instead of 50, okay? So, that's all I've got. Amazingly, I actually finished under time. So we have time for questions. This is where the slides will be later. Yes? Yes?
Why are the results different? Are they still inconsistent? Why is it so much faster?
Okay, the question, oh, sorry, I missed the last part. Yes, okay, the question was about the JSON Facet API, and if I can summarize, what the fuck? So specifically, the counts are sometimes inconsistent, things like that. So the JSON Facet API is kind of similar to the Pivot Facet API, except that it was written without this multi-stage refinement, right? The JSON Facet API historically has only done this part and then said, yay, we're done. Or more specifically, it's only done the merge alpha, right? It's done, I'm gonna go query both shards, I'm gonna add up those results, but where the question marks are, it kind of just assumes 0. Yannick has done work where now you can do two things that you couldn't do before, I think as of 7.0. One of the things you can do is you can say, you can specify this over request. So even though you only care about the top 10 returns, when it goes and queries multiple shards, you can say over request 50 or 100 so that it tries to get a better job. It tries to do a better job of identifying the what's it called in the terminology? The buckets, right? Do a better job of picking the top 10 buckets from the top 50 from each shard. The second thing you can do is you can pass a refine parameter, so that once it has identified the top 10 out of the top 50 from each shards, it'll actually do this beta request. What it won't do that, for example, pivot facility will do, or at least it's not clear to me if it'll do it, and when I asked the question, Yannick's eyes glazed over, is it won't necessarily recurse as deep as it needs to recurse over and over and over again. That's not necessarily a fundamental limitation of how it works. It's just not clear that it will do that if you have super deep nested JSON facets. There's also some things that you can express. JSON facets is, in my opinion, a shitty name because it's way more than facets. It's got like a stats language that you can embed in there. Some of those stats aren't necessarily easy to compute in a distributed sense. So I'm not sure if those will ever work, even mathematically, if it's possible. But in theory, it'll look a lot like this as it gets more work on the refinement, where you can say, go get me some stuff, and it'll do, request alpha, merge it, figure out what it needs to backfill. The refine option will do that. The big difference is just that facet.field and facet.pivot, refinement is mandatory. It always happens. Whereas in JSON, it's off by default. You have to explicitly ask for it. Yeah. But that is very new in 7.0, so if you're not used to seeing that, that's why. Okay. Other questions? Probably. Yeah.
And then it got split into two, as you explained. So that operation is happening on the replica where request receive on replica.
Right. So the question is, where is the work happening of being the coordinator and doing the I'm going to query multiple people and I'm going to merge the results back? That absolutely happens on whichever. I'm going to try and be very precise here. That happens on whichever core is part of the collection and ultimately gets the request. Which goes back to my example here, that if you have a round-robin load balancer across your entire Solr Cloud cluster, and you do a query for the tech products collection, and the round-robin load balancer happens to send it to host 3, host 3 is going to say, I don't have a core that can even handle that. I can't even guarantee that I have the plugin loaded for that search handler, right? So that's why the dispatch filter, without ever even parsing that HTTP request, acts as a proxy and forwards it to some node that Zookeeper says has any replica of any shard for that collection. Because at that point, we can be confident that whatever handler we need, whatever configuration we need for that collection, that's loaded there, right? So in this case, in our example, it forwarded it to host 4. It could have forwarded it to any replica. And then you could have initially made that request to any other node, and it would have said, yes, I have a replica of a shard. So that guy, he's going to act as this coordinator, and he's going to do that distributed logic. He's not going to look at his local index at all. He's just going to generate those shard requests to fan out and get those responses and merge them together. Okay? Yeah? It could, yes. I've generalized it here, but there's very little reason. I think there might be an optimization that says don't send work to myself unless I have to, because I think the idea is that you don't want to be burning your CPU while also blocking on yourself to burn your own CPU and use your own memory. I can't remember if that's actually in there, but I feel like someone told me once that it was. It generally tries to avoid itself, but it does, if I'm not mistaken, try to prefer cores on its own host. Right? So when the coordinator needs to talk to shard 1 and shard 2, if there is a replica of shard 1 locally so that it doesn't have to go over the network, I believe it does prefer that shard, but I could be wrong about that as well. It either prefers it or it actively avoids it. I don't remember which, and the math is confusing me right now. The lights are bright. Yes, last question.
So when it, on the next slide, when it requests facet, once the alpha step is done, when it knows that
Facet, you said, right? Yeah.
facet. Alpha step knows that I'm missing values for a certain values. So it will go and ask every shard, or it does.
No, It keeps track. In this case, because I focused on just 2 shards, it's a simpler example, right? Like in the math, it's question mark plus something, or something plus question mark. It knows whether it got values from shard 1 or shard 2 or shard 3. It's only going to bother asking the shards it didn't get the data from, which is why in that upper box up there, shard 1 is being asked for auto and food. Shard 2 is being asked for games. It only has to ask for the data it needs. But you'll also notice that, for example, like beach, clothing, and toys, they have question marks, but I don't have them included. And the reason is because their values are low enough in my hypothetical example here that we know they're not candidates. We know that even if beach has the highest value possible on shard 2, that's at most 90, which means beach's value is at most 94, which means beach's value is still not a candidate even if all of these other guys above it have the lowest possible value, because it'll still get beat out by like books and DVDs, for example, right? So that's the idea, is it's not just we have to go ask every shard for all the missing values. It's better than that. It's even better than we have to go ask all the shards for the values that they didn't give us. It's we have to go ask all the shards for the values that they didn't give us and might make a difference, right? It already does the math to figure out what values are in the realm of possibility to making a difference in my final count. And only those values are requested.
So assuming if, so just like food, if there are like 10 other values which were possible candidates to include, all of them would be asked.
Yes. Yes, yes. Yeah, so and that's where, in theory, there's a micro-optimization there as well, that maybe we should be returning more 0 values if possible, right? Like in this case, the idea was we had so many terms that they we couldn't possibly get them. But ideally, if the set of terms to be returned is very small, we might want to proactively, well, actually, no, you can't really do that. It depends on how much deleted terms you have. It's a whole implementation thing. But in theory, you might actually be requesting refinement on lots of terms that are just 0 by definition. And if you had some way to keep track of that, you wouldn't have to ask for them. But it's kind of hard to know what you don't know, right? It's kind of hard to say, I shouldn't bother asking about this because obviously it's 0. Well, why is it obviously 0, right? Just because that shard didn't tell you it was 0 doesn't mean it knew it. It could just mean it's literally never heard of the term food before, right? So, yeah. Okay, thank you, everybody. If you have any more questions, I'm around.